Solve the NLPP by graphical method. NLPP by graphical method. So problem is given as minimize z is equal to x1 square plus x2 square. Subject to constraint x1 plus x2 greater than equal to 4, and second 2x1 plus x2 greater than equal to 5, and x1 x2 greater than equal to 0. So this is the problem. We have a problem in minimization and constraint having greater than equal to sign. No issue. If problem is maximization, we have the less than equal to sign. So now when we are going to solve this problem by using graphical method, so in graphical method we have horizontal and vertical line. So that means horizontal axis and vertical axis. So correspondingly we draw the line. So first we draw, when we are going to draw the line, before we drawing the line we have to draw the horizontal axis and vertical axis. That means quadrant. So you know about the quadrant. So in quadrant we see that our inequalent, our decision variables are greater than equal to 0. This means that the region always lie in the first quadrant. The region always lie in the first quadrant. So we have to focus only on first quadrant. So no need to so we draw, this is the first quadrant. So that means here is x1 and this is x2 and this is origin. Now, so first we draw two axes, that means x1 axis and x2 axis, because we have, you can write the theoretical steps, so you can write. So we draw OX1 and OX2. And the region lie in first quadrant, because we have non-negative decision variables, so x1, x2. So this is the first quadrant, this is second quadrant, and third quadrant, and this is the fourth quadrant. So our feasible solution always lie in the first quadrant, because we have all the decision variables are greater than equal to 0. Now we have two inequality, that means x1 plus x2 greater than equal to 4, and x. So now we write same steps means we change inequality in equality, change or convert inequality in equality. So when x1 plus x2 equal to 4, so this gives us x1 plus x2 equal to 4, and the second gives us 2x1 plus x2 equal to 5. So 2x1 plus x2 is equal to 5. So when we change inequality into the equality, we obtain two equations. So we plot, that means taking a scale, we suppose this is 1, here is 2, 3, 4. Correspondingly, we consider 1 for vertical, 3 and 4. So 1, 2, 3, 4. So when we solve this, that means put x1 equal to 0 gives us x2 equal to 4, and put x2 equal to 0 gives us x1 equal to 4. So the coordinate for first equation is 4, 4. For second, put x2 equal to 0 gives us x1 equal to 5 by 2. 5 by 2 means 2.5. And put x1 equal to 0, put x1 equal to 0, so x2 equal to 5. So coordinate of second equations are 2.5 and 5. 2.5 and 5. So we draw. So we write this as x2 axis and take as 5 here. So 5. This is 5. 5. So 5 and 2.5. Second coordinate 2.5. That means x1 2.5. Here is 2.5. 2.5. So we draw this line. So this is the line which shows that 2x1 2x1 plus x2 equal to 5. And second line, where is the second line? Second line, x1 x2 4. So x1 equal to 4, this means x1 equal to 4 and x2 equal to 4. So this is the second line. So x1 x2 equal to 4. So this is the second line, x1 plus x2 equal to 4. So in optimization technique, we do these things. That means when we check the region where the region is lie, that means when we have the greater than equal to problems, so that means region above the line. So you see that. So the region is above the line. Above the line means this region. This is the region for below line, above the line. Similarly for second, so this line, that means this line also having the region above to the line. So common region, this is the common region for both line. This is the common region, that means outside. Now we move further, that means another step. So we use the so for objective function, we see that the objective function, what is the objective function here? Objective function is x1 square plus x2 square. You see that x1 square plus x2 square. Our objective function is x1 square plus x2 square. So x1 square plus x2 square. So we draw, that means take a radius of k, k square. So on the basis of radius, so we find out the concave or convex. So when we obtain the concave or convex, that means to check the gradient. So these are 2 points. Now we write the region. The region set it for the points here. This is the intersection point which is lie above the curve. That means, so we give the name of points x1 and x2, which cause the point lie on the region point at x1 x2, and the region is unbounded. The region is unbounded because there is no bounding. So this is towards to the infinity. So region is unbounded. So the region is unbounded, and we find out the convex feasible region. Convex. So we define also convex and concave, a curve upward or downward. So convex feasible region. So when we take x1 square plus x2 square, x1 square plus x2 square, and the region lies in the convex region. Lie in the convex region. That means x1 square plus x2 square. So the circle represent the circle. So the desired points of the convex region in the tangent. So we use the tangent to the circle. Tangent to the circle. So the gradient here, we find out the gradient of the tangent to the circle x1 square plus x2 square is equal to k. We assume that k. So we have the maximum or minimum z. So minimum z we assume that k. So is obtained by differentiating of the circle. So we can differentiate this circle with respect to x1. So we write as 2x1 plus 2x2 and dx2 upon dx1. So we find out the tangent line, that means dy upon dx, slope or tangent. So here y represent as x2 and x represent as x1. So this gives us dx2 upon dx1 is equal to minus x1 upon x2. So dx2 upon dx1 gives us minus x1 upon x2. So the gradient of the line, we calculate the gradient of the line. That means first line is x1 plus x2 is equal to 4. So what is the gradient of this line? How to calculate the gradient? Grade of f, grade 5, gradient of f, vector calculus. Del dot f, I del upon del x plus j del upon del y plus k del upon del z into f. So grade f, because this is constant, f is constant. So which is gradient of the line x1 plus x2, x1, so minus 1. So gradient of this line is minus 1, and tangent, that means first we find out and gradient of second line is 2x1 plus x2 is equal to 5. What is the gradient of this line? This line is also minus 2. So this line is minus 1 and this line is minus 2. So gradient minus 2. Now if the line x1 and x1 plus x2 equal to 4, so is the tangent of the circle. That means when we draw the circle, so make a tangent circle, when we draw the circle means that means the shape of the circle is in this form, that means this. So this only this line is touched with the circle for radius 2. You can construct the proper shape. So this is x1 plus x2 which is equal to 4. So that means so is the tangent of the circle, x1 square plus x2 square equal to k. So how to obtain the tangent? So then we obtain the tangent as dx2 upon dx1 dy upon dx equal to minus x1 upon x2 equal to minus 1. Gradient is minus 1. So here we see that x1 is equal to x2. x1 equal to x2. So second line, if the line 2x1 plus x2 is equal to 5, second line, so is the tangent of the circle, x1 square plus x2 square equal to k. So then dx2 upon dx1. So for this we obtain minus x1 upon x2 equal to minus 2. So gives us x1 equal to 2x2. So x1 equal to 2x2. So x1 equal to 2x2. So when we solve this, so that gives us x1 equal to 2 and x2 equal to 1. So first line, we see that the first line means x1 plus x2 is equal to 4. So touch the circle, x1 square plus x2 square equal to k at the point. So here we obtain the point 2 comma 2. So this is the point when touch the circle. So this point will be 2 comma 2. So this will 2 comma 2. So when we draw proper, so at the point 2 comma 2, and the line two x1 plus x2 equal to 5, touch the circle at 2 comma 1. So 2 comma 1 lie outside the 2 comma 1 lies outside the convex region. So it is not a desired solution. So the desired solution is 2 comma 2. So maximum z equal to 2 square plus 2 square is equal to 8. So for the value x1 equal to 2 and x2 equal to 2.